Okay, so we're going to do some more practice with K. It says, consider the following reaction, and I give you, this is a very heavily organic reaction, because look, you'll see there's butanoic acid, ethanol, ethyl butanoate, and water, and they do the experiment 3 different times, all at the same temperature, and they want you to calculate K, the equilibrium constant, and then comment on what you notice. So, okay, here's my reaction, right? So first thing you want to do is write an equilibrium expression. So K equals products over reactants. It looks like everything is a 1-to-1 ratio, so you don't have to do any sort of exponents because there's no coefficients. They're all ones. So products divided by reactants. And then again, they just did the experiment 3 different times. Now, remember the brackets mean concentration, and concentration means molarity, like moles per liter. If you notice in this chart, they only give you moles, which really just means you assume the liters are constant. So you're just going to straight plug the moles in there, meaning the size of the container is the same for all of them. So this guy, this methyl or ethyl butanoate is 20, right? In experiment 1. Water is 20 in experiment 1. Butanoic acid is 10. Ethanol is 10. 20 times 20 is 400. Divided by 10 times 10 is 100. 400 divided by 100 is 4. Okay, so that was for experiment 1. I guess I should do this. Experiment 1. So now we're going to do it again, but we're going to do it for experiment 2's values. So the ethyl butanoate is 10, the water is 40, the butanoic acid is 5, and the ethanol is 20. So I just used all of experiment 2's data right here. 40 times 10 is 400, 20 times 5 is 100, so the answer is 4 again. The constant didn't change, even though the amounts were different. Let's do it for experiment number 3. So experiment number 3, the ethyl butanoate is 12, the water is 10, the butanoic acid is 30, and the ethanol is 1. 12 times 10 is 120. 120 divided by 30 is 4. So the whole point of this is that if you reach equilibrium, you can reach equilibrium at different numbers. The constant doesn't change as long as you're at equilibrium. The only thing for that reaction that will change the constant is the temperature. Okay, so again, given equilibrium values, you plug into the equilibrium expression, solve for K. So now what we're going to do is we're going to work with ice charts again. Yes, they are back. The ice charts are for when you have like initial amounts and equilibrium amounts, and it kind of helps you organize all of your information nicely. We have used them for limiting reactant problems because it helps you organize them, and now we're going to use them for equilibrium problems. So let's just review really quick. The first thing you do when you have a reaction is you write out the reaction and you balance it. If you're doing equilibrium, after you write out the reaction, the next thing to do is to write an equilibrium expression. K equals products over reactants raised to their respective coefficient. And if you know all of your equilibrium, concentrations, you can plug into your equilibrium expression and solve for K. Plug and chug. This is what we just did. All right? Now, the next thing I'm going to introduce to you today is B, and then the last thing we'll do together is C. So B is where I don't give you all equilibrium concentrations. I give you some initial starting concentrations, and then I give you like a subsequent equilibrium concentration, and you work your way backwards to figure out everybody's equilibrium concentration that you can then plug into the expression to solve for K. So that's what we're going to work with first right now. So I have 4 moles of nitrogen reacting with 6 moles of oxygen. These are assumed to be initial amounts. These are your reactants. It's what you have initially, I, in the beginning. Now they're in a 4-liter container, right? And we want to do molarities. So we're going to turn all of these into molarities. Moles per liter. So 4 moles divided by 4 liters is 1 molar. 6 moles divided by 4 liters is 1.5 molar. And so these are initial amounts. And then I go on to tell you that you have 3 moles of NO at equilibrium. So I do know one of my equilibrium values. So this is where an ice chart is handy. But first, we need to write out the reaction. So we have N2 reacting with O2. In equilibrium with NO. And that's the balance. So there's my reaction. That's step 1. Step 2, write the expression. K equals products O raised to the respective coefficients divided by reactants. Okay. Now, until now, you were given this guy and this guy and this guy, and we plugged and chugged and solved for K. This one is a little bit different. So we're going to set up an ice chart. And a hint that an ice chart will be helpful is if you have initial amounts, like starting amounts. So remember, it was 4 moles per 4 liters, so that's 1 molar, right? And the oxygen was 6 moles per 4 liters, so that's 1.5 molar initially, starting out. And you should not have any product initially, because the reaction hasn't started yet. Now they gave you one more piece of information. They said at equilibrium, that's here, right? E down here, this row down here. At equilibrium, you had 3 moles of NO. Well, 3 moles divided by 4 liters is 0.75. 3 divided by 4, right? Molar. So we're going to use this number to work our way backwards to figure out all of these guys' equilibrium values. Why can't I plug this and this into here? Because they're not equilibrium values, they're initial values. And this is an equilibrium expression, and so you can only plug equilibrium values into it. So how does this work? Remember that your change row, this row right here, this is your stoichiometry row. This is where you do mole-to-mole ratios across the reaction. So here's the deal. If you didn't have any of this to begin with, and you ended up with 0.75 of it, I obviously gained positive 0.75 of it. That's the only way to do that. So the I row and the C row combine. This row and this row combine to make your equilibrium row. Well, you will use this change number. If you know how much of this was produced, you can do stoichiometry to go backwards to figure out how much of these reacted. Some of you can eyeball this. I'll show you it eyeballing, and then I'll show you it mathematically. This is a 2-to-1 ratio. So this number, whatever you have right here, should be double whatever number you have right here. Or you could look at it the opposite way. This number should be half of what this number is. But mathematically, this is what you're doing. You're saying 0.75 molar of NO was produced. For every 2 moles of NO produced, 1 mole of O2 react, because this is a 2-to-1 ratio. So again, this ends up being what? 0.375 right here. Now, the nice part is that the oxygen and the nitrogen react in the same ratio. This is a 1-to-1 ratio. So if this is how much I lose, right, because it's a reactant, that is also how much I'm going to lose of this reactant. Reactants lose in concentration and products gain in concentration. So now, to find the equilibrium concentrations of nitrogen and oxygen, you combine the initial value with the change value. I started off with 1 molar. I lost 0.375 molar, so I end up with, at equilibrium, 0.625 molar of nitrogen at equilibrium. Okay, and then the oxygen. I had 1.5 molar of it. It lost, or 0.375 of it was consumed. So 1.125 is left at equilibrium. Now that I have all of my equilibrium values, I take and I plug them in to my equilibrium expression. So the NO is 0.75. The N2 is 0.625. And the O2 is 1.125. Now, don't forget to square your top number. I'm going to give you a second to calculate it out, but you should be getting 0.8. So this is technically considered like K less than 1, right? So small. So this reaction at equilibrium tends to be favoring the reactant sign, right? Again, K is products. My gosh. I'm going to unplug this and plug it back in. Products over reactants. So a small K would represent higher concentrations of reactants at equilibrium than of products. All right. Yeah, I got the initial values so we could plug in molarity, right? These brackets mean molarity, by taking moles and dividing by liters, because moles divided by liters is molarity. All right. So let's try another one. So this one says calculations when initial and equilibrium values are given. So this is the same kind of problem. So go ahead and read it over. Give me 1 second. I need to get my charger. Okay, so we have a 1 liter flask, which is really nice to get molarity. 2 moles divided by 1 liter is 2 molar. I have 2 gases at the beginning of a reaction, so initially, and then they give you an equilibrium value of one of the gases present at equilibrium. They want you to calculate K. So here's my reaction. Set up the equilibrium expression. So K, oops, I want to do this in a different color. K equals products over reactants. And everything is 1 to 1 to 1, so that's really nice, right? So let's set up an ice chart. Why? Because I have initial values and I also have one equilibrium value. So 2 moles divided by 1 molar is 2 molar. 2 moles divided by 1 molar is 2, or 1 liter is 2 molar. No products initially. And then they did give me one extra piece of information, and that was that the NO was 1.3 moles at equilibrium. So that goes in the E row. Divided by 1 liter is 1.3 molar. So look, if I didn't have any and I ended up with 1.3, I must have gained 1.3. What's nice about this one is everything is in a 1 to 1 to 1 ratio. So if I gained 1.3 of this product, I will also gain 1.3 of this product. Now, this is still a 1 to 1 ratio, but reactants lose concentration. And then this will lose the same concentration, 1 to 1 to 1 to 1. So 2 minus 1.3 is 0.7. 2 minus 1.3 is 0.7. 0 and 1.3 is 1.3. So now I have all of my equilibrium values to plug into my equilibrium expression. I just take all of these guys and I plug them in respectively. So the SO3 is 1.3. And the NO is also 1.3. And the SO2 is 0.7. And the NO2 is also 0.7. So that equals K. So now we plug in chug. All right, and I'll give you a second to calculate that out. I think this is the answer. So this would kind of be termed as K greater than the number 1, meaning K is bigger. A larger value for K, the reaction is favoring the products. There are more products at equilibrium than there are reactants. All right, so this way to find the equilibrium constant is just a little bit more work because I didn't give you all equilibrium values. I gave you some starting values and then like one equilibrium value, and we had to work around that. This last one is going to be different from the other types of problems we've been doing, because in the other types of problems we were doing, we were solving for K. This type of problem, I'm going to give you K, so we're not solving for it. Meaning we're trying to find something else, like the concentration of something instead of K. So like when we solve for K, it's because we know all of the values in the expression, all the concentrations or all the pressures, right? Remember, we can plug pressure into there. Now, if I give you K, it probably means we're solving for one of the concentrations or one of the pressures. So let's look at this reaction. It says, what is the hydrogen ion concentration? And I give you 0.1 molar HF. So this is my initial concentration of HF. And I also give you K. So first things first, let's set up the reaction is written for you. It's HF. Remember, it's a weak acid, and weak acids go to equilibrium because they only ionize a little bit. So let's write out the expression. So it's K equals products, and everything is aqueous, so I get to include everything, over reactants. And everything was 1 to 1 to 1, so this is it. And again, they call this Ka because HF is an acid. And I actually know this number. It's 3.5 times 10 to the negative 4th. All right? Now, I have the weak acid going to equilibrium with its ions. And I'm going to set up an ice chart because I gave you an initial value of 0.1 molar. And then you shouldn't have any product initially, I. So the issue with this compared to all of the other ones is in the other ones, you either had all the equilibrium values off the bat, or then I gave you like one of the equilibrium values and you could work backwards to figure out what the other guys were using stoichiometry. I don't have any other information here. So because of that, you have to let X equal something. So you pick for your X, you pick a product, and you pick a product that you only have one of. And you let it equal that thing at equilibrium. So let X equal the concentration of hydrogen at equilibrium. I could have just as easily picked fluoride, F minus. When I say pick the one you only have one of, you pick the one that has a coefficient of 1. So here's what I mean. If I were to throw a 2 in front of this guy, you should not pick hydrogen. You should pick fluoride because there's only one of them. So that this is X and then this would be 2X. Otherwise, you're going to have fractions, and I personally don't like fractions, so I try to avoid them. I'm just giving you that as a strategy. So I just said I'm going to let X equal hydrogen at equilibrium. So for E, hydrogen is the letter X. So if I have 0 and I ended up with X, I must have gained X, right? Instead of a number now here, we have a variable. Well, this is a 1-to-1 ratio. So if I gain X here, I gain X here. So I end up with X. 0 and X is X. And then this is a 1-to-1 ratio, but this is a reactant, so I'm going to lose concentration. So this ends up being 0.100 minus X. And now you take these guys and you plug them in to the equilibrium expression. These are my equilibrium values. So the hydrogen ion concentration is X. The fluoride concentration is X. And then the HF is 0.1 minus X. Now, you can see up top this is going to be X squared, right? X times X is X squared, so I'm just going to rewrite that. And unfortunately, this looks pretty ugly like a quadratic to me right now, the way it's written. So we're going to do something to make our life easy, and here it is. You're going to assume that X is much smaller than the number you're subtracting it from. And in this case, we're subtracting X from the 0.1. Here's what I mean by that. Grab your calculator right now if you have it. Grab it. Type in 0.1. And then hit minus. And then I'm going to make up a really small number because this is what I'm assuming. I'm assuming X is really, really small. That's what I'm saying. So put in 0.1 minus 0.000001. I think I said 4 zeros and a 1. 0.00001. And you're going to get 0.099999, which is in essence 0.1, right? If you had to round it. So what this allows me to do is basically I'm saying X is so small that if I subtract it from this number, it won't really change this number by that much. So because of that, I can get rid of it. Now I can solve for X very easily without the quadratic. This assumption that X will always be small will always work in this class. It won't always work when you get to college, but it will always work for the sake of this class. So how do I solve for X? I multiply both sides by 0.1. That gets rid of it down here. And then I take the square root. And my X ends up being, I'll wait for you guys to do it. It's like 5 point, oh, I forgot. So 5.9 or 5.92 times 10 to the negative 3 is the answer. Well, I picked who I let X be. So that is what the hydrogen ion concentration, that's what I said it was. So hydrogen ion concentration is 5.92 times 10 to the negative 3rd, and concentration is measured in molar. X was also my fluoride ion. So it's the same number. Now, for the HF, I have to take 0.1 and subtract the X, 5.92 times 10 to the negative 3. And it does change it a little bit. .0941 molar. Okay, so these are my answers. Notice HF is drastically higher in concentration than the H and the F minus. That is because weak acids exist mostly as the intact acid as opposed to the ionized version of the acid. Now, it does dissociate a little bit. There is a little bit of concentration of this and a little bit of concentration of this. And because there are small concentrations of the ions present, it does conduct electricity a little bit, but it is a weak electrolyte because it's a weak acid. There aren't a ton of ions in there, okay? It's mostly this guy. Now, you don't need to know this right now, but I want to show you where this is heading. And this is why I was saying this is really important. They're eventually going to give you this problem and ask you what the pH of the solution is. So this is an acid, right? So hopefully we end up with an acidic pH, but I'm just going to show you really quick. I'm just doing a really quick thing. You don't need to know how to do this for the test. I'm just kind of giving you a heads up. There's an equation for pH. No, you don't have to memorize it. pH equals negative log of H, concentration. Because however much hydrogen concentration you have in solution determines the acidity of a solution. So, on your calculator, find your opposite button, not your subtraction button. You should have a negative button. And then hit your log button, not your natural log button, your log button. And we just calculated the hydrogen ion concentration, right? We said it was 5.92 times 10 to the negative 3. Right, that's what we said. The hydrogen concentration was 5.92 times 10 to the negative 3. So you take that, you hit your opposite button, log that number. What do you get? It's 2 point something, right? I'll wait. I don't remember what it was from last class. 2.23. Beautiful. Well, well, well. Does this make sense? Less than 7? I'll do this. If you're lower than 7 pH, you're considered acidic, right? This should make sense. This is an acidic pH because this is the problem for an acid. It's hydrofluoric acid. So it should have an acidic pH. And I'm just showing you this because this is where these problems are going. They're going to start off as ice charts and you're going to end up finding pHs and things like that. And then if I just got the question, if there were solids or liquids present in any of these equilibriums, you don't even put 0. You don't even include them in the expression. They're just not even a part of it. There's no number associated with them. Okay.